Om Swastiastu. Assalamualaikum warahmatullahi wabarakatuh. Salam nama budaya. In this video I will explain about chapter 10, Metallurgy for the Non-Metallurgist. But first I want to introduce myself. My name is Putra Hutabarat with student ID number 23055531075. I am from Mechanical Engineering Study Program from Engineering Faculty and Udayana University. Okay, next. Now, chapter 10, cast iron. In metallurgy, cast iron is an alloy consisting of iron, carbon, silicon, and other additional elements. One of the characteristics of cast iron, except why it is cast iron, is the significant content of additional element. Cast iron can be made with a variety of chemical compositions that affect its properties, such as strength, ductility, and toughness. Common types of cast iron include nodular cast iron, white cast iron, and malleable cast iron, each of which has specific applications in industry based on its properties. 10.1 Basic metallurgy of cast irons. Cast iron, which is also known as a cast iron, is an alloy of iron elements containing carbon or C, silicon Se, manganese or Mg, phosphorus P, and sulfur S. The carbon content in cast iron is usually between 2% and 6.67%, while steel has a lower carbon content, namely around 2%. The higher the carbon content in cast iron, the more brittle the cast iron will be. Cast iron are heterogeneous, multi-component, various alloys that solidify with additive. For example, when an iron with 2.5% Celsius is cooled below the liquidus line, picture 10.1, freezing begins first with the formation of austenite dendrites. Next, white and gray cast iron. White cast iron contains cementite, which dominates the iron mixture, resulting in a white color. The advantage of this cast iron is that it has higher durability compared to other cast iron because of its hard and strong nature. White cast iron is usually good cut using machines. Gray cast iron, also known as gray cast iron, contains graphite in the form of thin flakes that are evenly distributed throughout its structure. This causes the color and appearance to become gray. The advantage of cast iron is its ability to dampen vibrations and is relatively cheaper. However, the weakness of gray cast iron is its low mechanical properties, microstructure. In addition to the carbon-rich base, cast irons are gray, nodular, compacted, and malleable have a matrix steel structure that may consist of variable perlite, bayonet, martensite, austenite. These 5 basic matrix structures can be developed in any cast iron, although they are not necessarily always produced in typical commercial practice. Next, 10.2 Classification of cast irons. In metallurgy, cast iron classification refers to a system of categorizing cast iron based on carbon content and other chemical composition. Cast iron is an iron-carbon alloy with a carbon content of more than 2%. This classification helps in determining the mechanical and physical properties of cast iron, such as hardness, strength, and corrosion resistance, which depend largely on the chemical composition and microstructure of the material. For common cast iron, the range of alloying with carbon and silicon varies by the type of iron. Figure 10.10. As compared with steel, it is apparent that irons have carbon in excess of the maximum solubility of carbon in austenite, which is shown by the lower dashed line. The upper dashed line is the carbon equivalent for the eutectic composition. Next, 10.3. Gray cast iron. During the formation of the austenite dendrites, carbon is rejected into the remaining liquid. The carbon content of the liquid increases until it reaches the eutectic composition of 4.3%. At this composition, the remaining liquid transforms into two solids between points 2 and 3. In gray irons, graphite and austenite form. At point 3, all of the liquid is solid, and any further transformations take place in the solid state. After solidification, the eutectic cell structure and the pre-eutectic austenate dendrites cannot be distinguished metallurgically except by special etching or in strongly hypoeutectic iron. These graphite flakes are entrapped in the structure of solidification process, either as characteristic long-strain flakes, figure 10.12a, or in rapidly cooled sections as lumpy flakes with a star-like distribution, figure 10.12b. When the temperature has been lowered sufficiently, the remaining liquid solidifies as an eutectic structure of austenite and graphite. Generally, eutectic graphite is finer than protectic graphite. Next, 10.4. Ductile iron. Ductile iron, also known as nodular iron or spheroidal graphite iron, is very similar to gray iron in composition, but during solidification, the graphite nucleates and as spherical particles in ductile iron rather than as flakes. This is accomplished through the addition of a very small amount of magnesium and or cerium to the molten iron. Casting of ductile iron. Ductile iron is second only to gray iron in the amount of casting produced, account for over a third of all casting. Ferrous and non-ferrous ductile iron has the advantage in common with gray iron of excellent fluidity, but it requires more care to ensure sound castings and so avoid hard edges and carbides in thin sections, and it usually has a lower casting yield than gray iron. Next, heat treatment varies according to the desired effect on properties. For example, an cast pearlite microstructure can be annihilated to produce a ferritic matrix with lower hardness. Some of the applications for Austen-tempered ductile iron include gears, including side and timing gears, wear-resistant parts, high fatigue strength applications, high-impact strength application, automotive crankshafts, change sprockets, refrigeration compressor, crankshafts, universal joints, chain links, dolly wells. Next. 10.5 Malleable iron. The history of malleable iron goes back to Europe. The French scientist and metallurgist A.F. de Réaumur published the first technical discussions of malleable iron testing 1720 to 1722 in America. Malleable iron was introduced by Seth Biden, who knew of the white-hot malleable iron of Europe and foresaw a potential market for such a material. Figure 10.26 shows in the irregular contours of the tempered carbon from carbon decomposition and a variety matrix because the cooling rate from the malleabilizing temperature was very slow. With faster cooling, the matrix could be entirely pyrolytic. Malleable iron, like ductile iron, possesses considerable ductility and toughness because of its combination of nodular graphite and low carbon metallic matrix like ductile iron. Malleable iron also exhibits high resistance to corrosion, excellent machinability, good magnetic permeability, and low magnetic retention for magnetic fluids and brakes. The good fatigue strength and damping capacity of malleable iron are also usable for long service in highly stressed parts. Next. 10.6 Compacted graphite iron. Compacted graphite irons are the newest member of the cast iron family to be developed as a distinct category. Compacted or vermicular graphite iron have inadvertently been produced in the past as a result of insufficient magnesium or cerium levels in melts intended to produce spheroidal graphite ductility iron. However, it has only been since 1965 that compacted iron has copied its place in the cast iron family as a material with distinct properties requiring distinct manufacturing technologies. The applications of compact graphite irons stem from their intermediate position between gray and ductile irons. Compared to flake graphite irons, compacted graphite irons have certain advantages: higher tensile strength at the same carbon equivalent, which reduces the need for expensive alloying elements such as nickel, chromium, copper, and molybdenum. Much higher ductility and toughness, which result in a higher safety margin against fracture, lower oxidation and growth at high temperatures, less section sensitivity for heavy sections. Next. 10.7 Special cast irons. Special cast irons are typically high alloy irons, which can also be classified as either white or graphite irons. Figure 10.227. In gray and ductile irons, small amounts of alloying elements such as chromium, molybdenum, or nickel are used primarily to achieve high strength or to ensure the attainment of a specific minimum strength in heavy sections. Otherwise, alloying elements are used almost exclusively to enhance resistance to abrasive wear or chemical corrosion, or to extend surface life at elevated temperatures. Next, The oldest group of high alloyed irons of industrial importance is the nickel chromium white irons or Ne hard irons, which have been produced since about the 1930. They are very cost-effective materials for crossing and grinding. In the synthetic white irons, nickel is the primary alloying element because at levels of 3 to 5%, it is effective in suppressing the transformation of the austenite metric to PLA, thus ensuring that a hard martensitic structure, usually containing significant amounts of retained austenite, will develop even cooling in the mold. Chromium is included in these alloys at levels from 1.4 to 4% to ensure the solidification of carbides, that is, to counteract the gravitating effect of nickel. Okay, I think I can explain about chapter 10. If there are errors in reading, please forgive me. And the last I want to say, Om Swastiastu, Assalamualaikum warahmatullahi wabarakatuh, Salam Namo Budaya, and thank you for watching my video, and thank you.